So today we are going to teach you how to look at a pressure field. The effect of pressure is going to be most relevant to momentum conservation. So today we're going to start with what we already know about momentum conservation and derive the differential form of momentum conservation. We did a derivation last lecture based on Newton's second law, but this time we're going to do it purely from a momentum conservation point of view. And we are going to see why the pressure force is actually equal to the negative of the gradient of the pressure. Again, whenever we do control volume analysis, we draw a control volume in the flow field. And just as the mass conservation analysis we did last time, we are going to be drawing a rectangular control volume with a width of delta x and a height of delta y. Because we are doing two-dimensional analysis, we are drawing like a two-dimensional control volume. But you can always imagine we are drawing a three-dimensional control volume that extends into the screen with the depth of delta z. Okay, and at the end, if we can assume that the flow is 2D, which means the flow field does not change as you travel along the z direction into the screen, then all the delta z's that in the momentum conservation equation are going to cancel out, and you're going to get an equation that is purely two dimensions. Okay, so here, let's write down what we mean by momentum conservation. By momentum conservation, what we mean is that the derivative of the, let's just write in words, total momentum. Total momentum within this control volume. Again, let's denote the control volume with the capital Greek letter omega. Momentum conservation says that the time derivative of this total momentum is equal to two things, the summation of two things. The first thing is how much momentum is carried over by the flow into and out of the domain. Here we call this the flux of momentum across the boundaries. So here the boundaries are the four sides of this rectangle. And the second term is plus the external force, the total force. All right, and let's look into this case, what each of these three terms mean. So first of all, total momentum. We know that the total momentum is equal to the integral is equal to actually, if we think in three dimensions, it's an integral over this the three-dimensional control volume with a depth of delta z, right? It's an integral of the momentum, which is rho times the velocity vector. So let's actually, to make it a little bit easier to grasp, let's actually take the total x momentum so that we're going to generalize to all the momentums as a vector. But like in this case, let's just write the x momentum, which is rho times u times dx, dy, dz. All right. And in this case, rho times u is known as the momentum density. It's the density of momentum within the fluid. Okay, if you integrate the density over three dimensions, you get the total momentum. Okay, so now let's look at the second term, the flux of x momentum again. Across all the boundaries. Now it is equal to a two-dimensional integral across this boundary of this control volume. We call this partial omega. It's the boundaries of omega as a control volume. Okay, it is equal to the integral of the normal Okay, again, the normal here points outside, towards the outside of the domain. So it points to the left on the left, it points towards the right on the right, and up on the upper boundary, and it points downward at the lower boundary. So because we are talking about the influx, so maybe let's make it a little bit precise, the influx of momentum, and the normal points outward. So we are actually talking about the negative of n. So negative of n is the normal pointing inwards towards the domain. So because we're talking about influx, we should be using negative n dot with the velocity. So this negative n dot with velocity is basically how much volume of fluid is going into the domain per unit amount of time, per unit amount of area. So that's what negative n dot u actually dot, by our notation, this is capital V, right? Negative n dot capital V is the amount of flow volume going into the domain per unit time, unit area. And of course, this integrated over the area is the amount of volume of fluid going into the domain per unit time. Okay, and we have to multiply this by how much momentum is carried over by this flow. So we multiply this by the very momentum density we are looking at. And this integrated over, let's say, ds, s being the area, is the influx of X momentum.